Hi, welcome back. We're going to continue our discussion of enthalpy and potential energy curves by introducing some new concepts that we will unwrap in a little bit more detail in our next unit. But we wanted to kind of make sure you understand the whole of a potential energy curve. So if you noticed on those potential energy curves that there was always a peak. It wasn't reactants going directly down to products like this. All right, got caught up there. There's always a peak involved, not a trough. And what will happen sometimes if you're not careful when you're drawing these, you'll graph something incorrectly and draw a trough. These are never, ever, ever a trough. They always go up. So what happens in a chemical reaction is that all chemical reactions, in order for the reaction to go, the collisions have to have a minimum energy. And this minimum energy is called the activation energy. Now, the energy of the reactants is read right off of our graph. The energy of our products is also read right off of the graph. Up here, we have something called an activated complex. You should know both terms. It's a transition state because it's going to just go through the state. It's not going to stay there. And it's also called an activated complex. In an activated complex, and please remind me, whoops, that's not a Y. Please remind me to show you a little video clip of this online. All right, at this point, bonds that are going to break are partially broken. The bonds that are going to form are partially formed, and it's committed to going to product. Hasn't started yet. It's not rolling down the hill yet, but it's committed. It's going to go over the hill. Now, where students get mixed up is in understanding that activation energy is actually a difference. So you don't graph the activation energy. So we have our activation energy. In the forward direction, the activation energy is equal to my energy of the activated complex, you read that from the chart, minus your energy of your reactants, which we also read from the chart. So it's this difference here. I didn't draw that very well, but you get the idea. It's that difference there. Now, the enthalpy we already saw was our difference in energy, potential energy of our products, minus the potential energy of our reactants. And so this is my activation energy, and this right here is my enthalpy. You're probably going to see my cat in a minute because she's driving me nuts, climbing all over me. My husband likes to say my cats take me hostage as soon as I get home. All right, back to chemistry. Now, we can also talk about, let me put it up here, the activation energy for a forward direction. We just did that. Activation energy for the reverse direction. Some reactions we're going to find are reversible. We'll use a double arrow. And if it's a reversible, we take the energy of the activated complex minus the energy of the product. So let me get a different color to draw that on there to see if it'll be a little clearer. So from here down to here would be the reverse activation energy. Okay, let's take a look at some of these. Let's interpret some and draw some and see where we land on this. All right, now we're going to do a worksheet that I think is really, really helpful on these. And I don't know, maybe we'll come up with something fun and draw them on the tables or something like that, just to get some difference. All right, we want to label each and every one of these things on both diagrams. So first, let's start with the reactants. The reactants always come first. We always go reactants on the left and then products on the right. So both of these would be products. And that, if we read them off the graph, my potential energy of my reactants is 40. My potential energy of my products in this one is 20. In this case, my reactants are 10 and my products are 20. Okay. Now, the next thing it asks us to do is to do the activated complex. Remember, your activated complex is up at the top of the hill. So for my first one, the potential energy of my activated complex is 100. For this one, it's 50. Okay, so we've just directly put those on the graph. The other ones are all differences in energy. So let's take a look at what we have here. In the forward direction, my activation energy, I'm going to see if I can get a line here because that's just so not very neat. So let's draw a line instead. There we go. That is my activation energy for my forward direction. This is my activation energy for my other one in the forward direction. Should probably go over just a little bit to the right, but I think you get the idea. All right, I'll label these in a minute. Let me go ahead and draw the lines in. This is my enthalpy there. My difference between product and reactant is enthalpy. And just to keep it a little neater, in the reverse direction, this would be my activation energy in my reverse direction. Okay. Now, I want you to notice that on an exothermic curve, that the forward direction is exothermic, the reverse direction is endothermic. So we are always asking for the forward unless it's specified otherwise. So because the products are lower, we went down in energy, and this is exothermic. Because our products are higher in potential energy, we need to draw in energy from our surroundings, and it's endothermic. Our value, remember, delta H is energy of our products, which is 20, minus energy of our reactants, which is 40. So we get minus 20, which is what we should get for this graph. We should get negative for exothermic. Here, my delta, sorry, I put delta, oh, Dina, sorry about that. Let me see if I can erase some of that. Now, I put a delta E there, and because I've just been teaching in PreAP, or in AP, and we were doing that. I'm sorry, delta H is going to equal 20 minus 40, which is equal to a minus 20. Here, delta H is equal to 20 minus 10, which is a positive 10, which is what we would expect. Okay? Activation energy, don't graph the activation energy directly on the y-axis. Even though there's not a delta in front of it, it really is a difference. So I want to caution you, when students graph activation energy directly, that's when they tend to get a trough instead of a peak. So we just did delta H, that was that line and this line. Let's do activation energy. It's the energy of the activated complex. So that's my energy of my activated complex minus my energy of my reactants, because we're going to do forward direction. You always do forward unless it specifies otherwise. All right. So my reactants are at 40. So that's my energy of my reactants. Activation energy is always, always, always a positive value. And this is plus 60. So that's my activation energy in my forward direction. This would be my activation energy in my reverse direction. I'll let you calculate or determine what that one is. Okay? And my activation energy here is going to be 50 minus 10, so it's equal to 40. And we should put, whoa, sorry, it's jumpy sometimes. Get stuck. Kilojoules. I think it's actually my computer running around trying to multitask when it should be focusing on you guys. All right, so we graphed all of those. That's how you would, label. Let me do one final. We forgot to do our activation energy. This would be in the reverse. Okay, and this one is what? 50 minus 20, so it's 30. This one's 100 minus 20, so it's 80 kilojoules. Okay, look at your units. Don't forget units. Okay, so now let's take a look. Let's move on and actually have to draw one is our next example for this video. This time it says to sketch out a potential energy curve. So let me get a line here. So we need a line. Now you notice this is 50, 75, 150. So I'm going to go ahead and make some lines. Let's call that 100. This would be 50. This would be 150. Okay, so let me label those now with pen. So this would be 100. This would be 50. And this would be 150. Okay. Now, it says that the energy of my reactants is 50 kilojoules. So that's where my reactants are right now. My energy of my products is 75, which is going to be halfway up. Up. Did you notice I said up? That's a hint. Now, my energy of my activated complex, not my activation energy, my activated complex, I get to read right off the graph. So that's my activated complex right up at the top. Now all you have to do, once you've defined those 3 points, is just draw a smooth, and Mimio's never very smooth, but try to draw a nice smooth curve. All right, that's fine. You're not going to get graded for not having an uber smooth curve. Okay, cat hair in my eye. Okay, so you notice that, the energy of my products is greater than my energy of my reactants. Therefore, we went up in energy. If you go up in energy, it's an endothermic reaction. So we went up, and so it's 75 minus 50. So delta H is 25 kilojoules. Okay, it's endothermic because it's positive and it went up. We've got to gain energy to end up at a higher potential energy. The activation energy for the forward is this difference between here and here. So my activation energy here is 150. It's the activated complex minus the reactants. So that's 100 kilojoules. For the reverse, you start with the activated complex again, but this time we're going to subtract the products, and I get 75 kilojoules. Okay? So that's how you draw one of these. So until we get to have fun doing that in class, this is loving you always. Take care, kiddos.